So I'll be talking to you today about what I call the roots of analogy, relational matching to sample in pigeons, parrots, crows, baboons, and people. Now, I have many collaborators in this research because none of it was done here at Iowa. It was done with Joël Fagot at the CNRS in Marseille in France, who also collaborated and is now at Kansas State University. These were our baboon studies. Bob Cook at Tufts University, Anna Smirnova, Zoya Zorina, and Tanya Abozova. They're at Moscow State University. And we'll touch on these respective collaborations as we go. So if we go to the Descent of Man, Darwin's 1871 text, we see he had some considerable interest in the possibility of high mental powers in animals. And here he made the following observation. The greatest stress seems to be laid on the supposed entire absence in animals of the power of abstraction or of forming general concepts. Among these general concepts was going to be analogy, but both before and after Darwin, these abstract conceptual abilities of animals were central to philosophers' interest in the nature and evolution of human intelligence. The studies that I'll talk about, I'm calling them recent. They're recent compared to Darwin. The studies force us, I think, to reconsider the belief that animals lack any abstract conceptual abilities, and specifically abstraction among them is analogy. It's of particular importance for a number of reasons, one of which is that it's often been said to separate cleanly human from animal cognition. So what makes analogy interesting in general? Well, according to many theorists, including Deborah Gentner, Keith Holyoake, the essence of human reasoning and intelligence is based on analogical thinking. They claim that it's central to the study of learning and discovery, a key mechanism in creativity and scientific innovation. Analogies permit transfer across different concepts, situations, or domains. They're used to explain new topics and can serve as mental models for understanding any new domain. And these analogies are often used in problem solving and inductive reasoning because they can capture important parallels across different situations. Now, basic to analogy is said to be the appreciation of the relation between relations. And this claim was most strongly put forward by Roger Thomson some years ago. And in this specific context, a task came to the fore. And this task is relational matching to sample, RMTS. And in relational matching to sample, all of the logical arguments are visually provided. And the reason for this being important is you're not going to be able to use verbal materials for non-verbal animals. And so the fact that the materials can all be presented visually, it gives us a good lever to push in order to move forward with our understanding of analogical reasoning. As of 2000, the year 2000, only humans and chimpanzees had successfully learned relational matching to sample. And so we deemed it appropriate and interesting to see whether other animals might come on board. So in our collaborative research, we studied humans as well, but we included baboons. Joël Fagot has a great baboon facility in Marseille. We also included pigeons, not mine, but Bob Cook's, and parrots and crows, which were at the time in Moscow. So let's talk a little bit about the relation between relations. One kind of relation is said to be first order, and two or more stimuli can neither be the same as one another or different from one another. Second order relations, well, they're of a different stripe. They can also be said to be same and different, but it's the relation between relations that we're talking about. And just to be clear, here's a good first order relation. Here's another good first order relation. So the same baseballs were all the same, the crayons are all different. So to appreciate second order relations, we have to then take into account, let's say, groups of stimuli, one group, another group. If these are the same as one another and these are the same as one another, but not the same from one group to the next, the relation is nevertheless same. If a bunch of items are all different from one another and a different set of items, completely different items, are also different from one another, the relation between relations is the same. So there are two ways that you get to a same relation between relations. And if you have a collection of same items and a collection of different items, then of course the relation between relations is different. And just to pictorialize it, you know, the two flamingos, well, they're the same species. The tennis balls are all the same as one another. The feathers are all different from one another, and the piles of M&Ms are all different from one another. But when we talk about beyond the first order relations, the second order relations, now we have two ways to get a same second order relation. So same to same equals same, different to different equals same. So those are two different ways that you can appreciate that the relation between relations is the same. And using the same stimuli again, when you cross the other way, those relations are different, same to different, and same to different again. Okay. So I trundled to Marseille with a red card. I had an actual appointment for doing this work and went back and forth many times. This is the CNRS facility in Marseille. And this is the species we studied. This is one of the guinea baboons that the French have had in breeding colonies for a very long time. France occupied parts of Africa and colonized it. And there's been this interchange for many years. So they have a large breeding facility in the outskirts of Marseille. So the guinea baboons were our species. And we studied relational matching to sample in both baboons and people. The baboons had earlier learned the same different discrimination involving arrays of computer icons. This is a follow-up to the work that I had done with pigeons here. And there were 16 items in the arrays, and you'll see how they look when they're on the computer screen. The people didn't receive any prior same different training from us, but they obviously knew same different from their experience. And we set about to train them. We had two sets of items. It's important that you have different sets of items. One set of items could be used as samples. And when since set one were samples, then items from set two were choice or comparison items. That way, there's no identity relation. You have to use the relation between relations. And we interchanged the roles. So on other trials, items from set two, those were the sample items, and items from set one were the choice or comparison items. In training, those are all differentially reinforced, as I'll describe in a second. In testing, we now used two new sets of items, set three items. Do we have three? Yeah, and we have a new set of items. And in this particular case, they've never seen those items as samples before for set one choice or set two choice. So this was a test to see whether the concept generalized. Now, this is one of the guys working in the facility. They have a little peephole for their face to look through at the computer monitor. They could be lefty or they could be righty. There were two slots for their arms, and they had moved a joystick. This was a Georgia State device that Joel picked up. Nowadays, they're used touchscreens. But in any case, this was the setup. And the way the trial started, this is a fixation point. So randomly on the left or the right side of the screen, the baboon or the person saw an array of items. Those are all identical to one another. And then the choice was between, here's the fixation point again, not left or right, but above and below. And here the correct response would be to choose the other array that instantiated same, because that's what the sample was, and not to choose the one that had different items, okay, that were different from one another. And the top and bottom and the left right location of the stimuli was all counterbalanced. Same is true for people. They didn't get a pellet, a food pellet, but they did get a light or a tone to indicate that they were correct. A different trial looked altogether the same. There's an array of items. These happen to all be different from one another. When the baboon or person touched that, we moved to the comparison phase, and now the correct response was to choose the array of items that were all different from one another. Notice, of course, that the items in the testing array that are correct aren't the same items as in the sample array. So there's no opportunity for identity to play any part in learning. This is the most important thing to appreciate. So there was no real matching the sample. It's relational matching the sample. The relation among the items here different is what should guide your choice. Here, the relation among items should be what guides your choice, and that's be the correct one. So we trained the baboons. It took a long time for them to learn. We trained the people, and it took like no time at all for them to catch the gist of the game. And then we tested them. We tested them now with new sample items. And when we gave them new sample items, whatever they chose, we gave them correct feedback. So we use non-differential feedback. In every experiment we'll talk about here today, they're always correct insofar as the outcome of the trial is concerned, because we don't want to teach them the very thing we're testing, right? We're not going to explicitly train what we're seeing whether they transfer. So here were the two baboons, 3 and 8. One was a male, one was a female. There were 3 testing sessions. The gray bars are the training stimuli, and you see the baboons are doing well, between 80 and 90% correct here. And this is their performance to the novel sample items. It's about 70% correct. So there is some slight drop, but certainly above chance performance. People, well, what can we say? They know what relational matching to sample is, seemingly spontaneously. And it's nothing that we did in the experiment. It's probably their life experience that brought them to that point. So because of the work that we had done before with first order same different discrimination in baboons, we explored another couple variables. One was the number of items in the sample, and the other was the mixture of same and different items in the sample. Now, the number of sample items looks like this. This would be the same as the training arrays, but we would then reduce the number of items from 16 to 12 to 8 to 4 to 2. There's still the relationship, same and different, but there isn't as much, if you will, information that communicates that relationship. We found that this had a very profound effect on behavior in first order, same different training. We wondered what would happen in relational matching to sample. And this is what we found out. Let's first look at the people. There seems to be, as you reduce the number of items, there's some slight drop in accuracy, principally due to, I tried to get to one of the subjects where the accuracy kind of goes wrong. Oh, by the way, so there's this axis you have to appreciate. This is the percentage of times that the subject reports different. So when they see an array that's all different, okay, they should respond different. If they see an array that's all same, they should respond different. But now it's a very low number, okay? So these are highly accurate reports. The baboons look different. They look different. It didn't seem to matter much how many items there were in the sample when we gave them the relation same. but the relation different changed quite a bit. The baboons went from reporting different down to reporting same. And of course, this is a mind-bending outcome, one that it would take me another colloquium to explain or try to explain. But we believe that it has to do with the extent to which the animals are using the variability or entropy of the items in guiding their behavior. And it's perfectly clear that something very different is going on with the baboons and the people. And the same kind of issue pops up once again when we look at the mixture of items. Well, why are we looking at the mixture of items? Here's all same, here's all different. Why would we be giving these intermediate amounts of same and different? So here they're all different, all the same. Here there are just 2 different, here there are 4 different, here there are 8 different, here there are 12 different, here there are 14 different. And you can see that something is going on continuously. It scales up onto variability or entropy as well. And, well, that mattered differently for the baboons and the people as well. Let's look at the baboons. The baboons go from so entropy is 4 means they're different. So the score up here, that's a report of different, that's the correct thing to do. Down here, a report of that at the low level that's a same trial, entropy of 0. You see that there's high sensitivity on the part of both baboons to the amount of variability in the display. And the baboons are shifting from same to different midstream. Humans show a profound effect as well. They show intermediate levels of responding. They show sensitivity to entropy as well. But look at where they first cross, going from reporting different to reporting same. It's back here when there's any slight difference at all, they start shifting up. Okay, so when you go from no entropy to just the teeniest bit of entropy, boom, they're purists. If there's anything different in the display, they're on the way to reporting different. But the baboons scale similarly. So what did we learn from the baboons? Well, they learned slowly. They transferred, but with some decrement to new items, new sample items. Their accuracy fell with decreasing the number of sample items on different trials only. They were strongly controlled by variability or entropy of the sample. And they showed this very gradual shift from same to different. And this shift was near the midpoint where you might expect it to be if it was a continuous variable for them. People learned fast. They showed no decrement in responding to new items. They showed little or no deterioration in accuracy of reporting with decreasing numbers of sample items. They too were strongly controlled by variability or entropy of the sample. And they showed a very abrupt shift from reports of same to different. Anything slightly different from same, and they were on the way to reporting different. And this, by the way, fits closely with what we had seen in their performance on first order same different relations. So that's the baboon story. And now we go to the pigeons. And the pigeon research was done in Medford, Massachusetts, in Bob Cook's lab. And there's one of our subjects. They're looking at you. So in this particular experiment, the pigeons that we're going to be studying had previously been trained on a same different task. In fact, all the animals had some prior training. In their specific case, the pigeons had been given food whenever the same picture was repeatedly presented. So from like every 2 seconds or 3 seconds or 4 seconds, the slide would change, but it was always the same slide. They were getting food then. On non-reinforced trials, these were the ones where a different picture would show up. You'd go from picture 1 to picture 2 to picture 3 to picture 4. So it would be a different one. And they learned that. So they had some prior same different training. They weren't altogether naive. But that task has absolutely nothing to do with the task that they're going to be trained on. which is this. So here we go. This is the pigeon version of relational matching to sample. So the pigeon first sees a display, these 16 green things, they peck it, and the stimulus stays on the screen in training, and then they get a choice. Do you pick this one or this one? Well, the relation of all these items is the same, and therefore the correct response should be this. A different trial would look like this. Now the items are all different from one another. The correct response should be not that, but this. That's it. The birds get food when they're correct. They don't get food when they're incorrect. They get a correction trial instead. So after a lot of training here, these are blocks of 2 sessions. So this is the maximum number is over, like 50 days of training. But all 4 of the pigeons surpass 70% correct. Okay, so they learn. They're trained in this experiment, stay with me here, with just one set of items. So the same set of items appears, and from that pool, the test items come from set 2. But not as in the baboon experiment, there's no exchanging of roles. The samples always come from set 1. The testing stimuli always come from set 2. Why would we do that? Well, I didn't think it was a great idea, but Bob did, because what he wanted to find out next was what would happen if you now used set 2 items as the samples and set 1 items as the tests. This is a test for symmetry. So in addition to looking for transfer of relational matching to sample with novel stimuli, this experiment also included tests of symmetry. Can they go both ways? Can the same set of stimuli serve effectively as samples and tests? So this is the first test. Phase 1 is the symmetry test, and the birds bomb. They have no idea what to do. So they had been trained. They were upwards of 80% correct. They were doing really well when set 1 was the sample and set 2 was the test. But you flip it around, and they're a chance. I knew this was going to happen. This is why I didn't think it was a great idea to start there. But he confirmed what we suspected would be true. Now what happens? Now you go ahead and do this interchanging. Now set 1 appears as a sample and the test. Set 2 appears as the sample and the test. This is what we did with the baboons, right? Where we got pretty decent transfer. What happens when we do that? When we do that set expansion and then test with novel stimuli, these are the novel stimuli from now sets 3 and 4. You see that these are 1 and 2 in both directions. These are now tests with new stimuli serving as the samples. And now there is transfer. So after set expansion, you see some transfer. This is going in the right direction. This is good. Now, we do another set expansion. We take the set 3 stimuli that had been presented before sets 1 and 2, and we include them in the training set. So that's why there's boxes around them. Now they're getting more different combinations. If you want to learn a concept, have more variability in your examples. And when you do that, now you're up to over about 70% correct, which is getting up to where the baboons had been. So the training stimuli are about here, around 75% correct. And that now is an expanded set of training stimuli, a much expanded set. And then novel testing stimuli shown as samples, they're around 70%. So now we've gotten the pigeon to be a baboon, right? Now we're up in baboon territory. And the last thing that we included was one more symmetry test, not to bore you, but just let's see what it looks like. Now, when those stimuli that had only occurred as samples in testing for the first time also appeared as choice stimuli, now there was success. In the beginning, there was failure, all right? At the end, there's success. So this pigeon project showed some pretty interesting results. And since Bob and I had been working together on other experiments looking at the role of stimulus variables in same different discrimination, we did some more tests. So instead of having those neat little rows and columns of the stimuli, we staggered them, okay? So now there was less uniformity in the displays. And when we staggered the displays, there was very little effect. So the birds survived the staggering of the stimuli. We then did a test with a delay. Okay, it's a 0-second delay. And well, there was no effect at all. Then we did blurring. We blurred the stimuli, and we did it with simultaneous presentation. The sample is there while the choice is being made, or the sample goes away when the choice is being made. And now, this is what the blurring looks like. So if you're using just the coarsest aspects of the stimuli, you should be able to do just fine on this. This shouldn't be any problem at all. You wouldn't have any problem saying whether the top array had same items and the bottom array had different items. But you give that to pigeons and they bomb. If it isn't sharp and crisp, they just don't know what they are. And this has happened in one experiment after the other. So they do fine in the baseline trials, but these blurred testing trials, not so good. We then mixed the orientation of the stimuli instead of having them all pointed in the same direction. So now they're mixed orientation, and they're also staggered. How well did they do? They did just fine. They did fine whether there was simultaneous matching or just zero delay matching, when the sample goes off when the choice has to be made. And then we did one last test. We had different sizes of the same stimuli that had been presented before. We didn't think this would have much of an effect. Well, there was a surprise waiting for us. They dropped down quite a bit with the simultaneous presentation. In the successive presentation, they actually did as well or better with the sample gone. So overall, what did we learn? What did we learn overall? Well, overall, the birds learned slowly, but their transfer performance was enhanced by having more stimuli in the training set. It was also enhanced by having the same stimuli serve as both samples and choices. So when the stimuli served both roles, they did even better. And generally speaking, learning and transfer was not due to low-level perceptual mechanisms. This is something that we were criticized very early on and not having taken into account. Other experiments preceded this, suggesting that low-level perceptual mechanisms really played very little part, and that's what we found here too. So off to Moscow. Now, this is Lomonosov State University, Moscow State. And this is the subject. This is the European crow, Corvus cornix. They're, well, they have kind of a nice suit. It's not all black, right? It's more formal attire. And Amazon parrots, Amazona amazonica. These are cute little guys, but they were both given the same treatment. So I'm going to lump all the data together. There was nothing really to distinguish their performance. This was a really imaginative and terrific set of experiments. I had little participation in their design. So these experiments begin with training the birds to do stuff. And they were trained to do several things. They were trained on identity matching to sample with color, black or white stimuli, shape, black numerals that were Arabic 1s or 2s, different numbers of geometric items, 1 or 2 geometric items. So this was the, if you will, the elementary education that the birds were going to get before they went on to high school. And the way the experiment worked is there was a tray that was slid in front of the birds. They would then have to choose, in this case, the black or the white, because those match. This is identity matching to sample. It's not rocket science. And there were little worms there for them to eat. This is what the color task would look like. You would always choose black on the side if it was the sample. You would always choose white on the side if it was the sample. The same with shape, right? Wherever the 1 appeared, this is where you had to go. Whenever the 2 appeared, that's where you had to go. And the number of items, these happen to be shapes of different colors, but there was only 1 of them here, and you had to match the number. So go to where 1 is, or go to where 2 happened to be. Okay, so this is the initial pre-training. And then there was another important step in the experiment. Had they actually learned the matching concept from these 3 different steps, had they extracted a rule that then might be helpful to them when we got them to the relational matching to sample task. So we had gone through this pre-training, and now the birds were given novel items of different sizes, where they had to match the size of the item. And they were at 82% correct. So they had extracted this seeming rule of go to whatever is the same. They hadn't been trained with items of different sizes before, but they transferred. So this, the team thought was the right place now to step into the real experiment. Now, what is the real experiment? The real experiment is going to give the bird some altogether novel stimuli and choices. On some of the trials, there's a matching relationship, an identity relationship between the sample, which always involves 2 items, and the test stimuli, each of which also involve 2 items. And the best way to explain it is to look at it. But here's Anna with one of the crows, so that it's pushing aside the card. If you look carefully, it's pushing aside the card that has 2 identical shapes, okay? So there are 2 circles here, there are 2 squares here, and now there's a plus sign and a square. So this is a bird responding on the basis of the relation, okay, of item shape match, okay? A shape match here has to go with a shape match here. These shapes don't match. So this is the relation between relations, match shape, okay? So they now move into this step where there are some trials that are called identity trials and other trials that are relational trials. In relational trials, there is no identity at all that will guide their correct responding. But these identity trials, then when they're given, are differentially reinforced. You really have to see them to understand this. The relational, the key trials, the ones that'll have the boxes around them, these are the ones that are non-differentially reinforced. Remember I said back at the beginning, we always use non-differential reinforcement, so we're not explicitly teaching what we want to see. So here is what happens in testing. So here's a trial. There are 2 identical sized circles, okay? And look, there are 2 identically sized stimuli here too. Pick that, don't pick that. You get reinforced appropriately. Here again are 2 identically sized stimuli. Pick size here, don't pick it here because the sizes are different. Here's another case, the sizes are different. Don't pick that where they're the same, pick that where they're different. Now, there are 2 identically sized circles, but there are no circles in either of the choice alternatives. So the physical stimulus, in this case, the circle, doesn't provide any information, but the size does. So use size. Size then will guide you to the correct response. But it doesn't matter what the crow does on this trial or the parrot does. It always gets food. This is the key test. Okay, let's go down the next column. Shape. So here are 2 identically shaped stimuli. Okay, they are the same shape. They're 2 circles. Here are 2 circles. Okay, they're not the same color, but they're still 2 circles. These aren't 2 circles. Go here. Here are 2 differently shaped stimuli. Okay, okay. And this is where I get myself confused sometimes. Well, I knew I would do this. It's tricky for experimenters. It's tricky for subjects too. This is the one that keeps escaping me. Let's go here to color, see if I can retrieve my brain. My brain will work. There are these two colors, right? They match these two colors. Okay, they don't match these two colors. This is correct. Here are two colors. They match these two colors. That's correct. Here are two colors. They match these two colors. Those are correct. Here are two different colors, but they don't match any of the other colors. So the correct response, because they're different colors, is this one. Now, why am I messing up? Maybe the figure's wrong. I don't know. Maybe my brain is wrong. Maybe I should be a crow. So here are two different shapes. Here are two different shapes, but there's no match. None of the shapes are the same. So this is what you should choose on this trial. Okay, that would be the relational match. So here's the shape match. Here's the shape match. Never mind. Okay, you got it. These two shapes match these two shapes, even though they're different colors. So these are the special trials. Here, there's actual identity of the shapes that are to be matched. Here, there's two shapes that don't match, and they're the same two shapes here that don't match. Here, there are two shapes that match, but there are two other matching shapes, but they're not but they're not the right ones, because these are the shapes that match. So it's a tricky test, and the key data come from this. And if I go back to what I said before, where there's an identity relation possible to guide performance, the birds were at 75% correct. Where there is no identity except in the relation, they're at 73% correct. They do just as well. So all of these experiments in total, from pigeons to crows to parrots to baboons, they all show that they're capable of learning relational matching to sample, of transferring relational matching to sample, so that if relational matching to sample is basic to analogy, then analogy may not just be for people anymore. And that's my story.